Howdy. Today we're going to talk about things that are not quite crystalline, but definitely not amorphous as well. And we're going to start off by talking about liquid crystals. And liquid crystals are particularly important because they interact with light in interesting and important ways. Specifically, they can change the polarization of light. And so this is basically an image of shining polarized light through a film of liquid crystals. And you can see at some parts the light is basically rotated and slowed. Some part the light is canceled out because it's rotated, and it's rotated at an angle that's canceled out by the polarizer that is between the film and where we're looking at it. So that might seem like a little bit of an academic and not an interesting thing at all until you remember that a lot of technology is based on liquid crystals. So a liquid crystal display is basically something like a monitor or TV where we use a thin film of liquid crystal materials to turn on and off each pixel. And we do that specifically by changing their internal structure, changing how they're oriented so that it affects how they interact with polarized light. So we're going to start talking about what these materials are. This first video is going to basically focus on some definitions about what are liquid crystals, what are some of the different kinds of liquid crystals, and we're going to talk about short and long range order in these systems. And we're going to follow up by another video where we're focusing primarily on quantitative structural descriptors of liquid crystals. And again, the thing to think about is we're sort of occupying the spectrum somewhere in between amorphous materials and the fully crystalline materials that we've been talking about previously. So in order to get started, let's think about how we described these different systems before. And atomic crystalline solids, those are either things like metals or ionic solids, the individual components of that crystal structure are atoms. So in this case, this is an ionic solid, so there might be some cations and some anions, but the individual components are atoms. And the bonding between the principal components is strong primary bonding. And so in this case, that might be ionic bonding. In other cases, we might be talking about covalent bonding or metallic bonding, but the point is that this is very strong primary bonding. So bond enthalpies can be quite strong between individual atoms. So let's move on to think about a molecular crystalline solid. And so what do I mean by a molecular crystalline solid? In this case, the individual components aren't atoms, but they're molecules. And so this is an example of ice. This is one crystal structure that water molecules can take. Keep in mind, there's not just one kind of ice. Depending on the temperature and the pressure that you're at, there are dozens of different crystal structures that have been observed or proposed for ice. But the important thing here is that the individual components aren't atoms anymore, but rather they're molecules. And so that means that the bonding between these principal components tends to be secondary bonding. So in this case, there are relatively strong hydrogen bonds. If the molecules that we're talking about are something like methane, then it could be a weaker form of secondary bonding. But in general, it's a lot less strong than the primary bonding in the atomic solids that we were thinking about before. So the final question I have here is, what are the internal degrees of freedom? And by that I mean, how much freedom or flexibility does each of these molecules have? Can it have translational degrees of freedom? So could it be positioned there, or maybe a little bit to the left, or maybe a little bit to the right? Or does it have rotational degrees of freedom? So is this orientation exactly defined, or could this be free to rotate around some particular axis? And so in this molecular crystalline solid, we still have 0 internal degrees of freedom because there's no translational freedom. The positions of each of these molecules are are fixed in this unit cell, and there's no rotational degrees of freedom either. Each of these angles is determined, and the water molecule essentially is frozen. It's stuck in that one position. So this is a crystalline solid, but a crystalline solid that's made of molecules as opposed to made of atoms. So this is still very much what we've been talking about previously. This is a crystalline material. We would use the same terms, unit cells, lattice translation vectors, to describe this solid. Now this is different from what we're going to start talking about in this class. And these are called liquid crystals. And I know the phrase might be a little bit confusing because we see that word crystals again, but the important thing here is that they're liquid crystals. And so we got to talk about what does that mean. And let's ask the same question. So what are the individual components in liquid crystals? Ultimately, they're still molecules. So the individual components are still molecules, but we call them something different. We call them mesogens. So each of these long ellipsoids, it represents a molecule, but because it's part of a liquid crystal, we call it a mesogen. That's the basic building block of a liquid crystal. The bonding between mesogens, again, is relatively weak secondary bonding. So that means that there are not these stronger, more rigid primary bonds, but that gives it the property that now we can start to introduce internal degrees of freedom. And I'm just going to say greater than 0 or yes at this point. And we're going to talk about these different liquid crystal structures because they have different numbers of internal degrees of freedom. But just in general, you can see that, for example, in this nematic crystal, there is some translational freedom. If I look at one molecule and I look at the position of another molecule relative to that, this one is not fixed in a well-defined rigid point in space. There's some variability in terms of where that molecule could be. So there's some translational freedom. Rotational freedom, maybe these things are free to rotate around their long axis, but less free to rotate around some axis that's perpendicular to the long axis. So greater than 0 internal degrees of freedom, and the answer to that question is what we're going to focus on for a lot of the rest of the lecture today. And so building up, another way to think about these things is that liquid crystals, they occupy this space somewhere between liquids and crystals, and it's because there's a competition between bond strength, so how rigidly fixed is this position between one building block and another, and entropy terms, so that we know at higher temperature there tends to be more disorder in the system, and liquid crystals are kind of somewhere along this spectrum. So if we start off at a high temperature, things could be a gas, a very volatile phase, and so there's a lot of disorder in the system. As we start to cool down, gases will condense, they can form liquids, and so they're relatively more compact, but there's still a lot of disorder. And then traditionally, we think at some temperature, if we get low enough, that liquid will crystallize into a crystalline solid. And in a crystalline solid, the terms related to bond strength tend to win out over these temperature-based entropy terms. And so that means that there's not enough energy in the system to overcome the localized potential energy well that is fixing each of these units in place. Liquid crystals are kind of somewhere in between. They're somewhere in between the liquids and the crystals, and so we can say that they have a little bit less disorder than liquids. So in this particular case, things seem to be all relatively lined up in a particular direction, but they're not quite as ordered as a traditional crystal is. And so again, there are different kinds of liquids, and we're going to talk about the differences between these different types shortly. The very first level, we can classify liquid crystals by the shape of the molecule. And it's important to note that the shape is what gives it some degree of order. So things tend to, for example, if we have a rod-like structure, a long axis in a molecule, this is something that's relatively rigid, and so it wants to maintain a rod, you tend to have these kind of molecules lining up with respect to each other. Similarly, if I have a flat or planar molecule, it might make something that looks a lot more like a disk, and disks will tend to stack on top of one another, something like this. So we can classify these things into rod-like or calamitic types of liquid crystals, or disk-like or discotic. I tend to just use the simpler terms rod-like or disk-like. We can also have polymer liquid crystals, and so liquid crystal, again, there's these individual building blocks, the things that we called mesogens, and in a polymer liquid crystal, mesogens are either in the main chain of the polymer or they're appearing as side chains along a polymer backbone. And these, again, have unique properties because now the position and how these mesogens can stack is constrained by this backbone polymer itself. And finally, there's another pretty unique class of mesogens that we'll deal with later, and these are called amphiphilic. And so amphi means both, and philic means liking. So they're molecules that like two things, and the two things that they like are apolar solvents and polar solvents. So apolar solvents are things like hydrocarbons and oils, and polar solvents are things like water that have strong dipoles. And so because they have this sort of split personality situation, when you put a bunch of amphiphilic molecules into one kind of a solvent or another, they tend to organize themselves so that the tail or the head, the part that tends to interact with one kind of solvent or another, is exposed to the solvent that it likes. And a perfect example of this is a lot of detergents and soap molecules. The way these work, we think about the solvent that we use them in is water. You're washing your hands, and you put some of these amphiphilic molecules. Well, they'll tend to make little spheroidal shells around oil droplets and particles, and then they'll be washed away in the solvent. And so the reason detergents and soaps like that work is that they're picking up oils and residues on your hands or on clothing, and they're allowing it to be washed away in the solvent. Okay, so now we're going to talk a little bit more about these different classes of liquid crystals. And the two main ones are pneumatic and smectic. There's also cholesteric liquid crystals. These are also referred to as twisted pneumatic, and columnar liquid crystals. And we're going to ask these same basic questions of each of them. Do they have directional order? Do they have translational order? And we're going to focus on both sort of a short-range degree of order, so the molecules that are immediately surrounding that original molecule, and long-range order. So think of a molecule that's about 10 to 100 molecule lengths away from our central point. Do we still know something about the position or the orientation of that molecule in that same place? So pneumatic structures, the first question, let's think about short-range order first. Do they have directional order, and do they have translational order? And what do we mean by these terms? So directional order is, if I think about the molecules surrounding this initial central molecule, are they all pointing and aligned in the same direction? And so again, we have to be a little careful when we answer this question because it depends on what rotational axis we're talking about. So they all tend to be pointing in the same way, so they're kind of lined up. And so in that sense, if I think about an axis that's perpendicular to the screen, the rotation angle is pretty darn close between all of these nearby molecules. On the other hand, if I think about a rotational axis that is along the long axis of the molecule, well, they're relatively free to rotate around that rotational axis. And they're kind of unperturbed by the surrounding molecules. And so this is one where it sort of depends. I'm going to say yes/no. Yes, because if I'm looking at axes, they're perpendicular plane. Again, all these molecules are sort of pointing left to right, but they are free to rotate around that central axis. Do they have translational order? So let's think about when we're talking about amorphous solids. We know that there is always some degree of short-range order. If I see a molecule here, it's going to have nearest neighbors that are going to be some pretty well-defined distance away. And that's just because of the shape of the molecule and the surrounding molecules. So there is definitely short-range translational order. But by the time I get to a much greater distance away, we've lost that translational order. So I can't tell you anything about the exact position of this particular mesogen with respect to that starting point if it's some number of molecule lengths away. Directional order, again, they kind of have this overall direction that they're pointing in. And I think really we should focus on this one particular aligned direction. Usually we don't care too much about rotation around that elongated axis. So, there's an argument that under some circumstances you could say they're free to spin along their long axis, but really the thing that we're focusing on overall is the orientation of this particular rod. So we're going to go on and talk about the others, but I want to pause and I want to bring back up something that we had learned when we were dealing with amorphous materials, and that's this idea of a pair distribution function. So the pair distribution function describes the probability of finding a mesogen in a particular position. And one thing that's useful is to schematically draw the pair distribution function in two directions, either perpendicular to the principal director, so perpendicular to the direction that these are pointing, or along the direction, parallel to it. So we're going to do perpendicular first. Let's think about what does that pair distribution function look like if I were going to draw it perpendicular to this orientation that the mesogens are lined up. I'm going to give you a second to think about it. I'm going to go ahead and draw my axes while we're doing this. So, usually we say this is G of R. This is a probability distribution. And so 1 is sort of the average probability of being aligned in a particular direction. And this is a radial distance. And so we know, just like other molecules, there's some minimum position that these mesogens can't be on top of one of each other. And then there's going to be some average nearest neighbor distance. And that's going to be the maximum of this first peak. And then there's a little bit of an exclusion zone after that. And then I have my second nearest neighbor, maybe my third nearest neighbor. But after about that, we're going to hit our correlation length. This is chi, the Greek letter chi. Correlation length, remember, that's the distance after which we don't have any additional information about where the position of the next molecule would be. And so if I'm looking at it in a perpendicular direction, my plot might look something like this. Now I'm going to change colors here and draw the pair distribution function along the principal director. And what's it going to look like in that direction? One way to think about this is how's it going to vary from what I've just drawn? Do we have any additional translational order along this particular direction? The answer to that is no. Oops. Where we also are, relatively disordered along the principal director distance or direction. But there is one thing different, and that's just this nearest neighbor distance is going to tend to be a lot longer along that distance than it is perpendicular to that direction. So if I was going to draw the pair distribution function, and maybe I'll do it on the same axis, it would just be stretched out a lot more. I would still have a first nearest neighbor, a second nearest neighbor, maybe a third nearest neighbor, and then we would sort of flatten out. So in general, these share a lot of characteristics, but because the molecules are elongated, it's stretched out when I'm looking along that second direction. So this is my overlap. So this is the hard sphere radius, essentially, and the nearest neighbor direction along what we call the principal director. That's basically the vector that is lying along the direction that all these mesogens are pointing. Okay, so that was a nematic structure. Next, we're going to think about something called a twisted nematic structure. And in many cases, this behaves relatively similarly. Translational order, again, we'll have some short-range translational order, but we have no particular long-range order. Directional order, the only thing that's different now is that instead of all of these rod-like liquid crystals pointing in one particular direction and that direction staying the same, they tend to twist. So the principal director is changing in orientation, and the way it's pointing is a function of some distance. So this is shown as p here. And you can, in fact, you can describe the periodicity in terms of some sort of a sinusoidal function. And so we could say that the spacing between or the distance that it takes to do a full rotation is given by this 2 pi z over lambda term. So in terms of directional order, coming back here, they still have short range order, and I'm not going to talk about the fact that they could be rotated around that axis. Let's think about the way that the director is pointing. There definitely is short range order. There definitely is some long range order, but now that long range order is not static. The direction, rather than being fixed over space, the direction the molecules are pointing tends to twist over space. And that's why these are called twisted nematic structures. The next class is called smectic structures, and these are a little bit different. And the reason that they're different is because they have some additional translational order. So again, directional order, they tend to be pointing in the same direction as their surrounding molecules. If I go 10 to 100 molecules away, they're still kind of pointing in the same direction. They could be pointing perpendicular to these layers, or they could be tilted. So that's the difference between smectic A or smectic C. But the biggest difference between smectic structures, and if we go back to nematic structures, is that smectic structures have these layers that we don't see in the nematic structures. So I could call this layer 1, 2, 3, and the molecules tend to fall in one of those layers. And so what that means is that, while yes, they have some short-range translational order, they also have some longer range translational order because they tend to fall in a layer, although that is only in one direction. So if I think about a direction perpendicular to the layers, let's call this X, then I could tell you with some certainty positionally where these molecules are. But if I think about another direction, let's say a direction within a layer, we can call that Y, you don't have any additional information in terms of the long-range packing of these molecules. So they're restricted to layers. There's some degree of translational order, but they are disordered within a particular layer, and that's what this no refers to. So if we're going to do that same thing, draw that pair distribution function, if we were going to draw it perpendicular to the principal director, again, that would be, let me switch my pointer color, this red direction. That's going to look very similar to before. Because within a particular layer, I might have a nearest neighbor, a second nearest neighbor, a third nearest neighbor, and then I've hit my correlation length, and I don't have any additional order within a layer. But that's going to look very differently if we're thinking about a pair distribution function that is parallel to the principal director. And what that means is along the direction that these molecules are pointing, that's also perpendicular to the layers. And so as opposed to this first direction, now there's a pretty rigid periodicity where these molecules tend to find themselves either in a layer or not in a layer. And so I'm just going to say that this extends out some distance. And so these peaks are associated with the position centroids of each of these layers, where you're more likely to find the center of a molecule. And these valleys, let's call them X's here, are where I have a lower probability of finding the molecule. And that's the positions that are in between the individual layers. And these can extend, again, many, many hundreds of atomic lengths, so a significant distance. So it's fair to say that you do have some long-range order perpendicular to the layers, meaning that the molecules tend to be occupying positions within these layers. Columnar can be somewhat more complicated, and it depends on the actual shape of the thing that you have. And so again, we can have things like disks, we can have things like rods, things like rings, things like wedges. Again, these tend to stack on top of each other. And so in some cases, You might have some translational order perpendicular to the direction they're stacking, and you definitely have translational order along the direction of stacking, but that could be a little bit different. So, I think I'll leave this to you to think about, but you'd ask the same kinds of questions. Where do we see directional order, translational order, and how are these different from smectic structures? So I think I have a couple more points I'd like to wrap up with. We define these as occupying sort of this position between a crystal and a liquid. And the variable here on this axis is temperature. And so we can use temperature to undergo a transition between a crystal, let's say, and a liquid crystal. Or if I heated the system up further, I could go from a liquid crystal to a liquid. A phase change that is caused by a change in temperature is a thermotropic transition, or a thermotropic phase boundary. We can also have changes in their order based on a concentration of solvents. So how many solvent molecules, that's what these little purple dots are supposed to represent, per the concentration of mesogens. So a lyotropic phase transition is a phase change that's caused by a change in sort of a concentration of solvents. And so generally, you could think about this as, I have molecules that are dissolved in some solvent, and maybe I'm evaporating a solvent, and at some point, they're going to start to arrange in these liquid crystal structures. And I'm going to wrap up with this. The next video is going to talk about some of the quantitative measures of order in liquid crystal structures in more detail.